Okay, good afternoon. We have discussed about the interface boundary conditions in the previous lecture. Here you have to make one small correction. While I discussed about the conditions for the energy, while we have written this EL and EV. So EV was the total specific energy. Okay, so I had written internal energy plus kinetic energy plus potential energy. Instead of this internal energy, it should be internal energy plus P by rho L, and this jointly will be becoming equal to HL. Okay, so basically over here what we are doing, we are talking about the flow. Okay, so once we are talking about the flow, what it means, whenever we have some flowing stream, then along with the internal energy which is associated with thermodynamic properties, we also have one more property which is called as flow work. Okay, and internal energy plus flow work comes together as nothing but enthalpy. Is this point clear? All are clear with this point? Okay, so basically whenever we do talk about the total specific energy, then we will be having actually enthalpy. Okay, all are clear with this point? So you have to make one correction, that instead of writing this total specific energy as internal energy, you have to write it enthalpy. Why enthalpy? Because we are considering that in this control volume, this liquid mass is actually entering and coming with some energy. So when it is flowing, then along with the internal energy, it will be having flow work also associated with it. Is this point clear? Then this is the correction. Now let us talk about the remaining things. So we had started our discussion on the fluid particle shapes. In terms of fluid particle shapes, we had sessile drop, sessile bubble, pendant drop, pendant bubble, and a floating bubble or drop. Okay, and we started discussing about the pressure difference. I told you that in the scenario of stagnant liquid, basically all these shapes will be outcome of the balance of pressure forces and the surface tension forces, because interface is there. So at the interface, surface tension force is acting and there is gravity. So because of the gravity, of course, there will be the hydrostatic pressure variation. Okay, now if this is my origin point and this particular direction is positive y, then I can say that density of this drop is rho p and density of surrounding fluid is rho. Okay, so depending upon the change in height in the vertical direction, my change of hydrostatic pressure will be rho p minus rho into g into y. Is this point clear? So rho p minus rho into g into y. All are clear with this point? All are clear? Now at this point, at any arbitrary point, what is the pressure because of the surface tension force? Pressure because of surface tension force is sigma times 1 by R1 plus 1 by R2. Is this point clear? So sigma times 1 by R1 plus 1 by R2 is my pressure force. Is my pressure difference because of the surface tension force at any curved boundary. Now let us talk about this starting point. At the origin point, if I am measuring y with reference to this position, then y will be equal to 0. So if y is 0, then the corresponding value of the hydrostatic pressure difference at this point comes out to be 0. Is this point clear? Now if you calculate the pressure difference because of the surface tension at this point, at this particular point, whatever is mean radius of curvature in this particular plane, same will be mean radius of curvature in the other plane. So R1 will be equal to R2 and let us consider it is equal to R0. All are clear with this point? So it means the pressure change because of the surface tension at this point will simply become 2 sigma by R0. Okay, that is pressure because of the surface tension. But ultimately, because we have to balance this pressure with the hydrostatic pressure, and corresponding to this point, the pressure because of the surface tension should also be balanced in such a way so that its value comes out to be equal to 0. Okay, so that's why whenever I will be balancing this hydrostatic pressure variation, I will be writing it 2 sigma by R naught minus 1 by R1 minus 1 by R2. Now if you see in this equation what we have, at this point what is the value of y? 0. So when y is equal to 0, this whole term left hand side is equal to 0, and at point O, R1 is equal to R2 is equal to R0. So once I am substituting this, then my right hand side is also becoming equal to 0. Is this point clear? So it means the balance of hydrostatic as well as the surface tension force is becoming in such a way so that at point O, the hydrostatic pressure difference and the surface tension pressure difference are becoming equal to 0. Now, when I will be moving away from this point on the interface, so say I am at this point. When I am at this point, what is the change in y? Change in y is negative. So if change in y is negative, then rho p minus rho g into y, and y is negative, so this value will be negative because I am now talking about a drop. So if I am talking about a drop, then density of particle is greater in comparison to density of the surroundings. So this term is positive and this overall term will be of negative magnitude. Okay. When the overall term can be of negative magnitude, if value of R1 and R2 is low. Is this point clear? If value of R1 and R2 is low, then 1 by R1 and 1 by R2 term will give the larger value in comparison to 2 by R0, and overall quantity will be becoming negative. Is this point clear? So it means that whenever I move away from the origin point on the interface of a pendant droplet, what happens? The mean radius of curvature of the interface decreases. All are clear with this point? Okay. Anyone is having any doubt? If I consider this point for a pendant drop, for pendant drop what will be happening? This is y equal to 0. Whenever I will be moving in upward direction, what will be the value of y? It will be positive. Okay. So once I am having positive value of y, then this overall quantity will be positive. Okay. Overall quantity is positive. Now, in order for the right hand side to be positive, value of 2 by R0 has to be greater than 1 by R1 minus 1 by R2. Okay. So for this value to be positive, R1 and R2 should be high. Okay. So it means the pendant droplet shape adjusts in such a way that when we move away from the origin on the interface, its radius of curvature actually increases. Is this point clear? So this particular equation can be considered as the equation for droplets and bubbles under the stationary condition, which gives the balance of the surface tension and the hydrostatic pressure forces. Okay, and this balance is actually responsible for a particular type of shape which we are actually obtaining. Is this point clear? All are clear with this idea? Just a moment. प्लीज आप कॉल करिए, जो नंबर दिया है आपको उसमें करिए. ठीक है, मैं आपको दूसरा नंबर मैसेज करूँगा. Just a minute. Okay, so now these are the experimental shapes of particles. So here you can see this is the experimental photograph of a spherical bubble. Okay, and once your bubble grows in size, then what happens? The shape of the bubble distorts, and this is the photograph of a corresponding ellipsoidal shape. Okay, so when the bubble takes the shape of ellipse instead of a sphere, then it is called as ellipsoidal shape. Okay, then this particular shape you can see is in the form of a, if I consider entire to be a sphere, so this is the top portion of the sphere. Okay, so this particular shape is called as spherical cap shape. Okay, so earlier whatever the shapes I have discussed, these are the shapes when a fluid particle is actually resting on a solid surface in the presence of the surrounding immiscible fluid. Now these are the shapes when fluid particles are in motion. Okay, so typically when the size of the fluid particle is very small, then what will be happening? The interfacial drag force will be less in order to deform the shape of the particle, and particle will stay in its spherical shape because of the surface tension force. Okay, but whenever the size of the particle will be growing, then ultimately what will be happening? The surface forces because of the surrounding fluid will be dominating. Okay, and because of these dominant forces, what we will be finding? We will be finding that the deformation in the shape will take place and bubble may reach to the ellipsoidal shape. Okay, after ellipsoidal shape, what we can have? We can have spherical cap shape. Okay, so in case of spherical cap shape, what will be happening? I will be having actually adjustment in such a way so that it looks as part of the sphere. Now under what conditions these different shapes are obtained? Let us try to see over here. Yes? That is what actually what we have to do. We have to visualize. Okay, and based on the visualization, whatever geometry we are able to fit in there, that we will be calling as the particular option. Okay. Ankit, is it clear or not? Now what happens whenever we have a confined wall? So earlier whatever the shapes I have described, these are in the surroundings of an infinitely large medium. Okay, for example, if I have this room and in this room I am considering a small bubble. But what if I do? If I bring the walls of this room close to each other, then what will be happening? So we will be actually putting that particular fluid particle in an confinement or zone of restriction. Okay, so once we put the particle in confinement or zone of restriction, and if the volume of the fluid particle is sufficiently high, in that scenario we will be finding that volume will be accumulated in this particular shape, where the top will be in the form of a spherical cap and back will be in the form of a long cylindrical volume. Okay, so this type of shape is particularly called as Taylor bubble. All are clear with this idea? Now, corresponding to these different scenarios, F, G, H and I, different fluid combinations and their corresponding properties are given. Okay, so here you can see this particular bubble is again spherical cap, but it is having some dimple at the tail. So this is dimpled spherical cap bubble. This particular shape here you can see it is like this. At the center it is having presence of surrounding fluid. So this is called as skirted type bubble. Okay, and this is a particular bubble with large number of surface oscillations. Okay, so large number of surface waves are actually present in this wave. So depending upon the corresponding properties, first is Idvos number, or it is also called as bond number. Okay, bond number is nothing but delta rho g d square, where d is the length scale divided by sigma. So it is the balance of buoyancy and the surface tension forces. Okay, second is Morton number. Morton number takes into account different properties of the fluid medium. For example, it is accounting for viscosity, it is accounting for density difference, density of surrounding fluid, as well as the surface tension forces. Okay, so all the properties, when these are combined together to form a dimensionless parameter, that we are calling as Morton number. And third important parameter is our Reynolds number, rho dEu by mu. Okay, so in the presence of these, we can have different shapes, and this is a standard flow design map which can actually give the shape of different fluid particles whenever these are present in the fluid mediums. Okay, so here you can see on the abscissa, on the ordinate we have Reynolds number, along abscissa we have Idvos number, and in between this line is there which is for Morton number. And all these plots are actually logarithmic axis. So this axis is also logarithmic and this is also logarithmic. So these are log plots in order to account for the variation of large number of properties. Okay, so here you can see we have one particular design where Reynolds number and bond number are actually small. So when Reynolds number and bond number are small, then size of particle is so small that it will be almost remaining in the spherical shape. Okay, and once you increase the size, then you will be finding the occurrence of the ellipsoidal shape. Okay, and if you further increase the liquid inertia, okay, so almost at the same bond number, it means you are not much changing the size, but you are changing the Reynolds number. So at very high Reynolds number, what will be happening? The inertia forces will be dominating. So inertia forces will try to introduce some oscillations at the periphery of the bubble. Okay, so these oscillations will give a particular design which is called as wobbling bubble design. So in case of wobbling bubble design, what will be happening? The bubble will not stay in any particular shape, it will keep on oscillating with time. So this type of shape is called as wobbling bubble design, and particularly if we have to improve the mixing and heat transfer characteristics between the fluid particle and the surrounding fluid, then this can be one of the good combination, because it will be improving the mixing near the interface. Okay, and here when our bond number is very high and at low Reynolds number, we can have dimpled ellipsoidal cap where we have the shape in the form of ellipse, but at the tail this is distorted. Okay, so it is having some dimple formation. So that's why this name is given as dimpled ellipsoidal. And once you slightly increase the Reynolds number, the bubble will be in the shape of a skirted bubble. Okay, and finally, if you have very high Reynolds number, then you may find that your bubble will take the shape of a spherical cap. Okay, and ultimately we have to remember one point, that this particular curve is applicable when gamma and k are not large. Okay, so what is gamma? Gamma is ratio of density of particle to the density of the surrounding fluid, and k is ratio of viscosity of particle to the viscosity of the surrounding fluid. Okay, for example, if you consider a situation that you have a highly viscous fluid particle. So if you have a highly viscous fluid particle, then mu p will be very large in comparison to the viscosity of the surrounding fluid. Mu, in that case value of k will be very high, which will be approaching almost to infinity. So if value of k is very large, that particular type of fluid particle will be having very less deformation. Once it is having very less deformation, then this type of plot cannot be referred. Is this point clear?
सर ये नॉन डायमेंशनल नंबर चेंज करने पे ये शेप क्यों आ रहा है? रीजन क्या है शेप?
That is what I am saying. So in this case, what you have? You have the size of the droplet so small that if you have low Idvos number, what it means? Idvos number is nothing but balance of delta rho d square by sigma. Okay, so in the numerator this is gravity or buoyancy forces, and in the denominator it is surface tension force. Okay, so when your Idvos number is less than 1 or close to 1, corresponding to that, which force will be dominating? Surface tension. So once surface tension is dominating over the buoyancy, it means shape of the droplet will be made spherical. So this point is clear. Now if you grow the size, you are growing the size in such a way Idvos number is reaching close to 10 and Reynolds number is also high, close to 10. In this scenario, what will happen? Now once Idvos number is large, it means buoyancy force is significantly high in comparison to the surface tension force. So if buoyancy force is high, it will try to elevate the bubble at the faster pace. And at the same point of time, your Reynolds number is also high. So Reynolds number is high, it means inertia of the bubble is also more in comparison to the viscous forces. Okay. So once the driving force, buoyancy force is high, it will cause high velocity, and corresponding to that velocity, the commensurate viscous forces are low. So there can be deformation in the shape. Okay, so bubble will be, or fluid particle will be actually susceptible to shape changes, because viscous force will not restrict the inertia force. Okay, so that is the reason it is getting the ellipsoidal shape. And once you are maintaining almost the same Idvos number, it means buoyancy is not changing much, but bubble inertia is increased. It means viscosity of the surrounding fluid is further decreased. So then Reynolds number is more high. So it means the dissipation of the energy near the interface will be low. So if dissipation is low, then interface will be having so many interface oscillations. Then we are going to the wobbling design. Is this point clear? Likewise, when bond number is very high, close to 100 or 1000, in that scenario, what you have? The size of the bubble. Ultimately, for increasing the bond number, what has to increase? This equivalent diameter. So it means size of the bubble has to increase. So size of bubble is so high initially that it is flattening from the front. Once it is flattening from the front, it is taking the shape of the ellipsoidal bubble. Okay. And once it will keep on flattening much, and say fluid inertia is also high, Reynolds number start increasing, then what will happen? When this bubble is rising in upward direction, surrounding fluid from the top will be displaced. Is this point clear? Once surrounding fluid is getting displaced, then it will be creating some circulation pattern at the leading edge, at the trailing edge. So this circulation pattern will lead to entry of the surrounding fluid into the bubble, because of which it will occupy this type of skirt. And if you further increase the inertia, then this circulation will be so high that it will not be able to maintain this stable lamella which is protruded from the bubble. This lamella will be breaking in the form of small satellite bubbles, and only a spherical cap will be staying at the top. Is this point clear? So like whatever the shapes we are getting, these are corresponding to the relative comparison of the Idvos number, Morton number, and the Reynolds number. Okay, so it means buoyancy, first we have buoyancy and the surface tension force. So once buoyancy is dominating over the surface tension, it means droplet will not be staying spherical, and it will be rising at the faster pace. And after that, again we are comparing the Reynolds number, which gives the relative combination between the inertia and viscous dissipation. So if inertia is high, corresponding to that, the dissipative effect will be less. So once dissipative effect is less, then oscillatory effects because of the inertia change will be large. Okay. And another point I told you that this particular plot is only applicable for finite values of gamma and rho. Because if I have extremely large value, then what will be happening? Like I explained in the case of viscosity, if viscosity of fluid particle is very large in comparison to the viscosity of the surrounding medium, then fluid particle, in order to deform the fluid particle, it will be having so high dissipation that we have to invest good amount of energy. Okay, so that is the reason that deformations in the fluid particle will be less, because it will be resisting all the deformations. Okay, it will be almost consuming maximum amount of energy. So because of this, these particular shapes may not be obtained.
सर जो बॉन्ड नंबर है उसमें ग्रेविटेशनल फोर्स भी है.
Yes.
तो वो मतलब कि उसका इफेक्ट
Yes, so the effect of the gravitational force or buoyancy force is to increase the velocity of that particular medium.
सर बायनेंसी पर
Ultimately what will be happening? Say you have a bubble, okay, so because of the weight of the bubble will be in the downward direction. Okay, so weight of the bubble will be density of fluid particle into its volume into g. Now you will be having some buoyancy force which is acting in the upward direction. What is buoyancy force? It will be density of the surrounding fluid into volume into g, because this is fully submerged inside. Now what will be net effect? Net effect will be Fv minus W. So that's why I am using over here delta rho, where delta rho is density of particle minus density of the surrounding. Okay, so this is the net outcome of buoyancy and the weight. Okay. Okay, all are clear with this point? So this is some preliminary idea about the shape of fluid particle. Of course, whenever you will be doing testing on large number of parameters, then there will be different shapes available for the fluid particles. Okay. Now let us start the new module, which I told you earlier that after going through the introductory discussion, we will actually move towards the second module, which will be on experimental techniques. Okay, so now we will be starting our second module, which is on experimental techniques. So before starting the module on experimental techniques, let us first try to understand the need for experiments. So can you tell me what is the need for experiments?
न्यूमेरिकल सॉल्यूशन अगर कन्वर्ज नहीं कर रहा है फिर टाइम इसका काफी टाइम लगेगा तो उसके लिए एक्सपेरिमेंट करके देखना फायदा होता है.
So one need can be whenever you propose any new theory or any hypothesis, either through theory or numerical simulations, then what you need to do, you need to validate that. That is first point. Second point also has come from your side, that if you have to numerically simulate any phenomenon, then it takes huge amount of time, significant amount of time. But the commensurate experiment of that particular phenomena will be very fast. For example, if you have to simulate bubble rise in a tube, okay, so bubble rise in a tube of 1 meter length, if you inject a bubble at the bottom, in say 5 seconds or 10 seconds, it may reach from top of the bottom of the tube to the top of the 1 meter height. But if same phenomena you have to repeat through computer simulation using any of the computational method, it may take, say, if you have very high-end computer, then it may take 1 day or 2 days to simulate the phenomena for these 10 seconds. But if your computer is not very high-end, then it may take even a week or a month to simulate that particular phenomena. Okay, so computational simulations also take good amount of time. Okay, so first thing is there is a need in close working with the experimentalists, theoreticians and numerical analysts, so that we can attack the problem from all the aspects. That is first point. Second important point is, experiments are always necessary to verify the reliability and limitations of both mathematical models and numerical codes. So in terms of pure theoretical analysis, what we do, for example, if we have to only simulate flow through a pipe, we make so many assumptions. For example, Newtonian fluid assumption, then fully developed laminar flow assumption, then steady flow assumption, then flow is entering parallel to the pipe. So many assumptions we have made. And in terms of numerical simulations also, though we can actually analyze the developing flow through numerical simulations, but in numerical simulations also we have some associated errors in the form of discretization error, etc. Okay, so numerical solution is also not foolproof, like it's not 100% accurate. There can be some situations like in micro scale flows where the magnitude of the error, approximation error, may be so high that it is giving wrong interpretation of the results. Okay, so there can be issues of reliability in terms of numerical simulations, and in particular theoretical analysis we can have limitations of so many so many assumptions in order to simplify the mathematical equations. Okay, so if we have to test or verify the reliability of mathematical models and the numerical simulations, then what we need to do, we need to perform the experiments. Sometimes we do not have the sufficient theoretical background to understand any particular phenomenon. Okay, so many times this also happens. Say experimentally we are observing something, but in theory we do not have sufficient idea that which type of additional physics introduced in the terms of mathematical terms may explain that particular behavior. Okay, so any new phenomena if you have to capture, then experiment could be a good starting point to understand the behavior, and based on that you can introduce some theoretical concepts to understand that well. Okay. Particularly, can you give me some idea, when we do theory, what we does? Assumptions we are taking, but on what basis we take assumptions? First we have physically seen that phenomenon, that this is what is happening, and by that physical understanding of the phenomena we make assumptions and try to understand it theoretically. So the similar way, if you have to understand any new phenomena, so first starting point could be the visualization or understanding of that phenomena through experiment, and then we can introduce the different terms in theoretical understanding to actually analyze that phenomena theoretically. For example, if you start with boiling, so anything you consider, in boiling what people have initially done. So the initial study includes where some person has, particularly Nukiyama has studied the cool boiling on a nichrome wire. Okay, so he has taken a nichrome wire, some experimental facility where he started adding the heat, and after that whatever phenomena has come, initially he visually tried to represent that phenomena. After that multiple experiments have been done, and then people have derived the semi-empirical model. Later on people have tried to enter into the minute details of the boiling phenomena, that how bubble generation takes place at the nucleation site, then how that bubble grows in size, then how that bubble departs from the surface. So depending upon that understanding, then they have actually developed the theoretical understanding. Okay, so it means that if any new thing you have to observe, so experiment could be the starting point. Okay, so after visualizing that particular experimental situation, that physical phenomena, then you can slowly think towards the theoretical or numerical direction, that how you can theoretically or experiment or numerically actually mimic that experimental phenomena. Okay. So whenever we deal with the multi-phase flow, in case of multi-phase flow we have presence of many peculiar quantities. For example, in single phase flow, pipe flow, we will be having no presence of the interface. Okay, but in case of multi-phase flow we may have the presence of the other surrounding medium, and that may present in any way, like it can be a well separated flow, it can be a fully dispersed flow, it can be a mixed combination, that part of the pipe is well separated, part of the pipe is dispersed. Okay, so if we have this type of complex situations, then in theoretical analysis our assumptions may not be sufficiently able to capture the full dynamics of that particular phenomenon. So that's why the theoretical analysis may not be foolproof, so we may have to go for the experiments. Okay, so whenever we have to do experiments, what we need to do? What we need to do? We need to analyze some quantities. Okay, so in case of multi-phase flow, if we have to analyze the different quantities, the very fundamental quantity which we need to analyze is called as void fraction. All are clear with this point? Now you have understood, earlier I have given the name to this quantity void fraction as volume fraction. Okay, so what I told you, that if we have to do it on the volume basis, then we can say volume in a particular pipe section, volume occupied by the gaseous phase divided by total volume is, say, volume fraction or of the gaseous phase or void fraction. Okay, now, and I also gave you some idea about the localized void fraction, that void fraction is not always a global parameter, it's also a local and instantaneous parameter, because at a particular boundary of control volume, at any time there can be, say, in this portion fluid 1, in this portion fluid 2, at some other time in this portion there can be fluid 1 and in the remaining portion there can be fluid 2. All are clear with this idea? Now, void fraction is a parameter which keeps on changing with time. Okay, and which keeps on changing also with different locations. So it is having significant variations in different portions of the domain which we are considering. So to understand this, we have to first, or to experimentally measure this, we have to first make some mathematical background, so that based on that mathematical background we can design the measurement system with the help of which we can measure the local and instantaneous variation of void fraction. Okay, so first mathematical function we are defining as phase density function. Phase density function pk is having two arguments, one is x, other is t. So this x over here you can see is bold, so it means it is representing the vector quantity, so it's a position vector, and other is time. And this particular phase density function is having two values, 1 and 0. 1, if position vector belongs to set dk, if, and 0 if position vector does not belong to set d. So what we can have, say this is my domain. In this domain, this is phase 1, this is phase 2. Okay, now k can have two values. One will be, when it is referring to phase 1, then k will be 1, when it is referring to phase 2, then it will be 2. Okay, and the portion which is occupied by fluid 2, it will be becoming d2, and the portion which is occupied by 1, that will be becoming d1. All are clear with this point? Now if I consider that my phase density function p of 1 corresponding to position x comma t, such that this x belongs to d of 1. What it means? X belongs to d of 1, it means my position vector is somewhere in the domain of fluid 1. All are clear to this point? So corresponding to that, what should be the value of phase density function P1? It should be 1. Okay, if your position vector is belonging to d of 1, then your value of phase density function at that particular location for phase 1 should be 1. And if your position vector is not belonging to D1. It means your position vector is somewhere here. So if it is somewhere here, then value, it means here there is no fluid 1 present. So corresponding to that, value of phase density function should be 0. So are you clear with this point? So it means that phase density function for kth phase is a function of position as well as time, and if the position vector is pointing in such a way so that it belongs to domain of k, then its value will be 1, otherwise its value will be 0. Okay, so it means you can say that it is nothing but an indicator function whose value becomes 1 whenever we are referring to a particular fluid, and it becomes 0 within the domain where that particular fluid is not present. Okay, now let us talk about local void fraction. Local void fraction means at any particular arbitrary location we are trying to measure the void fraction. Okay, local void fraction of gaseous phase epsilon g. So g I am referring to, it means I am talking about the gaseous phase. So typically, if I am having the liquid and gas present, then void fraction we typically refers to the volume fraction of the gaseous phase. Okay, so over here I am saying that volume fraction of the gaseous phase or void fraction of gaseous phase at any particular location x comma t. Now you have to see, I am not using small t, I am using capital T. What is the difference? I will explain you. Will be equal to 1 by capital T integral over capital T P of g x comma t into dt. First important point is, when I am writing epsilon g at x comma t, it means I am referring to any arbitrary location x. Say this is my location x. Okay, now in this location x, if flow is happening, and if say these are my number of bubbles which are coming towards this location x, then what will be happening? If I plot P of g as function of time, then initially is there any gas? Is there any gas? No. Say these are gas bubbles and everywhere in the surrounding I have liquid. So is there any gas initially present in this? There is no gas, so initially the value of P of g will be 0. Whenever this first bubble will be crossing this location, then corresponding to this P of g will become 1, and when this first bubble is crossing, then the liquid behind it will come, then again it will become 0, then again 1, 0, 1, 0. So like this it will keep on changing. All are clear with this point? Whenever I am referring to a particular location, at any particular location, if multi-phase flow is happening, then at that particular location, at some time there can be the gas present, at some other time there can be presence of liquid. So corresponding to presence of gas, phase density function of gas will become 1, and corresponding to presence of liquid it will become equal to 0. Okay, now if I consider that this number of cycles I have plotted over large amount of time, capital T, such that it is, so capital T is what? It is the large time period. Okay, such that this capital large time period is able to account for the number of fluctuations which are taking place in the phase density function. Okay, so good number of fluctuations it is accounting for. Then if I do integral over that large time period, then I can say that whatever output I will be getting, that particular output will be almost average representative for that particular time period T. Is this point clear? All are clear with this point? So that is the reason when I am defining this particular phase fraction, I am calling it as local void fraction. So local void fraction at that particular location. All are clear with this point? Now one important point you have to note that if my value of T is less, then what will be happening? if value of t is less, say I have kept my t close to 5 seconds, then in 5 seconds I may get, in first experimental trial I may get 3 such peaks. Okay, in second experimental trial I may get 5 such peaks. In third experimental trial I may get, say, only 1 peak. Okay, so every time whenever I will be doing experiment by using the value of t equal to 5 seconds, my number of peaks in the phase density function will keep on changing significantly. So if these are keep on changing significantly, my value of local void fraction will also keep on oscillating. Okay, but instead of this, if I take a large time period, say 20 seconds or 30 seconds, and when with large time period 20 or 30 seconds, I will be doing one trial, say I am getting 15 peaks. When I am doing second trial, I am getting 12 peaks. In next trial, I am getting, say, 16 peaks. Now, with reference to this large time period, whatever the change in phase density function will be there, that will be actually less. So, because of which the fluctuations in the local void fraction will be decreasing. Is this point clear or not? Okay. So, if you have a large sampling time, then all the type of fluctuations will be accounted for. And if you repeat that experiment again and again, you will be almost getting the same average value. But if you consider a very small time, then all the random fluctuations may not come into the sample, and every time if you repeat the experiment, you will be finding different values. Okay, so that is why when we are defining the local void fraction, the selection of this sampling time t is actually important. And how sampling time changes the value of the local void fraction, that is plotted over here. So here you can see sampling time in seconds, starting from 0 to 100 seconds, and this is the corresponding fluctuations in the local void fraction. Yes. Okay, so here you can see initially the fluctuations are high in magnitude, and whenever the time is increasing, fluctuations are decreasing, and finally after a sampling time of 50 or 60 seconds, the fluctuations are so small that it can be considered a single unique value. All are clear with this point? Okay, so how to measure local void fraction, or what is the meaning of local void fraction? Did you understand? Local void fraction means you have pointed a particular location, and at that particular location you have taken a finite sampling size so that it is able to account for all the fluctuations which are taking place in the phase density function, and time average of that particular quantity will be giving you a unique average representative of void fraction at that particular location. Okay, now you can see that whenever in the next step I have written this formula, I have only written it in terms of capital X. So time is dropped, because if my time period capital T is sufficiently large to account for all the fluctuation, then every time you do the measurement you will be getting almost the same value. So it will not be time dependent, then it will become independent of the time. So that is the reason I am calling this value as local void fraction. If this value is not independent of time and changing with time also, then I have to call it local instantaneous void fraction. All are clear with this point? Local means I am referring to particular location, but at that particular location also, at each and every time it is keep on changing. So then it will become local instantaneous void fraction. However, local instantaneous void fraction is not of much use, because flow will be so uncertain that every time you cannot record the data. So always whenever we do try to approximate data on say large time periods, because whenever this type of application you will be finding in, say, chemical industry or other application, then we are not operating that particular device only for, say, 5 seconds or 10 seconds. We are operating that particular device for long running duration of say 24 hours, or even in case of process industry, the devices keep on continuously running. Okay, so once the devices are continuously running, we have to define the average representative of the samples. So that's why instantaneous measurement is avoided and we are defining it as local void fraction. All are clear with this point? Now next is one-dimensional void fraction. What is the meaning of one-dimensional void fraction? You see the mathematical formula and then you try to explain me. Epsilon g comma L or comma 1 is written to say it is one-dimensional, and now it's a sole function of time and it is equal to 1 by L integral over the L phase density function of the gas xt as integral over the L. What is the meaning?
We are determining the variation within a certain length in a particular period of time.
Yes. So, for example, situation is, this is the pipe. In this pipe, I have these bubbles. Okay. Now, from here to here, say my length of pipe is L. And this photograph of the pipe is at some time T1. Okay. So at T1, what you will be getting phase density function? Here it will be 0, then 1, 0, 1. Exactly in front, this is as function of length. So exactly in front of the bubble, it will be 1, and away from bubble, it will be 0. Okay. So it means that the integral of the phase density function over the length, what it will give me? This integral will be 1 corresponding to bubble and 0 everywhere else. So it will give me the length of the gaseous phase at that particular time divided by total length over which we have done the measurement. All are clear with this point? Now, this pipe is having this particular photograph at some time T1. Corresponding to some time T2, I may have bubble distribution something like this. So then corresponding to that, this value will be changing. Okay. So that is why I am calling this as one-dimensional void fraction. And this one-dimensional void fraction is nothing but instantaneous. This is an instantaneous measurement. All are clear with this point? Then what we have, two-dimensional void fraction. Epsilon G2 T 1 by A integral over the A rho G xt. So this is nothing but a area averaged quantity. So in case of area averaged quantity, what I will be getting? Say these are my bubbles and remaining is liquid. So phase density function will be 1 corresponding to these bubbles and rest everywhere it will be 0. So if it is rest everywhere 0 and I am doing integration over the area, so this integration will give me area of gas bubbles at any given time T divided by total cross-sectional area of that one. Fine. Similarly, if I have to measure the three-dimensional void fraction, then it will be nothing but my volumetric integral. All are clear with this point? But you have to remember that all these three quantities are having functional dependence of time. So it means these quantities are nothing but instantaneous one-dimensional void fraction, instantaneous two-dimensional void fraction, and instantaneous three-dimensional void fraction. Okay. If you have to find out the time averaged of these quantities, how I can find out? I can define epsilon G1 as 1 by T integral over the T and then 1 by L integral over the L Tg x comma T dl and outside this. All are clear with this point? So first I have taken the line integral, then I have taken the time integral. So now it will become one-dimensional time averaged void fraction. All are clear with this point? Likewise, I can define two-dimensional time averaged void fraction. Okay, all are clear with this point? So it means that if you have to design some experimental technique for measurement of the void fraction, what you need to do? Mathematical basis we have seen. Okay, but in all these mathematics, what is missing? Phase density function. All are clear with this point? So it means if you can devise some experimental setup which can measure the phase density function, then you can calculate the value of local instantaneous and the time averaged void fractions. All are clear with this point? So by having this mathematical understanding that how phase density function can be utilized for measurement of void fraction, now we have to go to the next level, that is to devise experimental ways in order to determine the phase density function. Okay, so how to calculate phase density function using experimental techniques, that I will discuss in the next class.